Hello, in this video we're going to be looking at section 9.3 where we introduce derivatives. So we start out by discussing an average rate of change. Now an average rate of change of a line would be the slope of the line. So if you think about a graph that has 2 points labeled on it, the first point has an x value and a y value, the second point has an x value and a y value, then the slope would be y2 minus y1 over x2 minus x1. But if you label the points a and b, the notation just looks like what you see here on the graph. Now, what this formula will do is it would tell you the average change in the function from one point to another point. But what it will not do is it can't tell you the instantaneous rate of change at a specific point. So eventually, later on in these notes, we will be wanting to figure out how quickly is this function changing at the point A. And right now, the only thing that we have, the only algebra tool that we would have to approximate that is we could figure out the change from A to B, and then that might be an approximation of the actual rate of change or the actual slope at point A. But as you can see in this diagram, the slope of this pink line and the slope of this black line don't really look like they would be very similar at the point A. So we might say it's a bad approximation, but it would still be an approximation of the slope of the graph of f at the point A. But before we get too far ahead of ourselves, let's look at an example where we compute average rates of change. Suppose the total cost in dollars of the production of X printers is given by this cost function. We want to find the average rate of change of total cost when production changes over a couple different intervals. So on the homework assignment, the notation is going to actually look like this. And the implication is that the first x value we're interested in is 100, the second x value we're interested in is 300. So if you see something like this with brackets, that's just a closed interval from one x value to another. Well, we have already talked about how you come up with an average rate of change. It's simply the slope of the line between 2 points. So I like to think about it in terms of like the definition of slope, y2 minus y1 over x2 minus x1, although you're welcome to write it in terms of a and f of a, b and f of b. Now in order to do this, okay, this is for part A, it may help me out to actually list what the points are. One x value is 100, and I don't know the associated y value. And then if I plug in 300 to the graph, I don't know what the associated y value is yet. So I'm going to take a little bit of time in my calculator and figure out what the y values would be if I plug these two x values into the cost function. Now, having done that, we can plug these values into our slope formula. 14,550 minus 5,950 over 300 minus 100 is going to be something over 200. Looks like it's 8,600, and then when you divide those, you get 43. So this is an average rate of change. We might want to label our answer. The label of the answer would be dollars per unit. You can think of this as you had dollars in your numerator and then units in your denominator. So dollars per unit. I guess we could more specifically call it dollars per printer in this example. All right, we've answered part A. Let's go on to part B. We're going to do the same process here. So in the text, or in a homework example, you might see it reference this interval as 300 to 600, which is neither here nor there. We would like to write down the two x values. We need to compute the y values. I've already computed it for this first one, but let's go ahead and put the 600 into the calculator. And we get 43,200. So then m is equal to y2 minus y1 over x2 minus x1. And let's see what we get. Looks like 28,650 divided by 300 is equal to 95.5, again, dollars per printer. So when we interpret our results at the end, we have to be very careful how we word this. The number 43 is the average rate of change of the total cost. So this is not the average cost of producing 100 printers or 300 printers, but how did we compute this? We computed the cost of making 300 printers, subtracted the cost of making 100 printers, so this is an increase in cost, and then we don't divide it by the total number, we divide it by how many we have just increased by. So it's the increase in cost divided by the increased number of printers. So 43 is the average increase in cost per printer if we increase our production from 100 to 300. Another way of saying that is that if I increase production from 100 to 300 printers, then my average increase in cost per printer is $43. Now, if you want to do like a little mental exercise to like really get your hands on like what this number means, you could start at 100 and start plugging numbers into the cost function. So when you plug in 100 into the cost function, you'll find that it costs us $5,950 to make 100 printers. So then plug in 101 and see what your number gets, and check to see how much different are these two numbers. So your cost will increase, but it's not going to increase by $43. It's going to increase by some smaller amount. And then you could plug in 102 and see how much that increased by. So what's the difference between 102 and 101? And that cost would increase, and you'll see that it progressively gets a little bit more expensive every time we make a new printer. But if you average out all of those results from 100 to 300, what we would get is we would get an average increase of $43 per printer. I'm not going to take the time to write out a sentence for part B, but we could write something very similar. The increased production from 300 units to 600 units will result in an average increase in cost per printer of $95.50 per printer. All right, we are ready to discuss instantaneous rates of change. So the goal of what we want to do is we want to develop a formula or some kind of method to compute the instantaneous rate of change of a function at a particular point. And the point we're going to pick on is x. Now, if we are looking at an x value, we would know that its corresponding y value can be computed by plugging it into the function. So f of x is the corresponding y value. Now, algebra does not give us a tool to compute an instantaneous rate of change, so what we would have to do initially is we would have to approximate the rate of change of the function. We can do this using the average rate of change process that we've just discussed. In order to do that, we need a second value, a second x value over here. And the important thing about this second point is we want to measure the distance it is away from x. So we're going to say that this is h units away from x. So if I move h units to the right, then my new point is just going to be x plus h. So that's the x value of the second point, x plus h. If you wanted to compute the y value that corresponds to that x value, you would have to plug x plus h into the function. So f of x plus h is the y value that corresponds to x plus h. Okay, now that we have our hands on 2 points, we can draw a line between them and compute the slope. Let's draw this in green here. Here's a line, and we could compute the slope using that same formula we've used before, y2 minus y1 over x2 minus x1. Except now that we've labeled our points in this manner, where h is the distance between the 2 points, we can use those numbers, those values, in place of y2, y1, x2, and x1. So it would look like this. We have y2 minus y1 over x2 minus x1. And if you're tracking with this, it's y2, y1, x2, x1. Now, this expression can be simplified just a tiny bit. In our denominator, what we see is we see x plus h minus x, and then certainly x minus x would reduce to just be 0, and all we would have left is h. So the expression reduces to f of x plus h minus f of x over h. Now, what we've said is that we've said this computes the slope of this green line. And the slope of the green line is not very similar, visually it just doesn't look very similar, to the slope of the black line, the original function, at this point x. It's kind of similar, but not all that similar. How could our approximation be improved? Well, if we took this second point and we allowed it to migrate closer and closer and closer to the first point, if these 2 points are really close to each other, then what happens is that the slope of the green line would look really similar to the slope of the function at that point. So our approximation can be improved by letting h approach 0. All right, well, what would happen then is m would be equal to the limit of this expression we just developed, and it's the limit of that as h approaches 0. So this was the reason why we spent time in previous sections talking about limits, because we want to be able to compute this thing. And what we have here is going to eventually become the definition of the derivative. So we call this an instantaneous rate of change of the function, or just the rate of change of the function. One thing I want to point out, if you think back to how we think about limits, what would happen if you tried direct substitution right out of the gate on this expression? Well, if you put 0 in for h, then suddenly this first part just becomes f of x, and then it would be f of x minus f of x, which would be 0, all over, and then when we plug in 0 for h, it would be 0. So you get 0 over 0, and what we know about that is that this is an indeterminate. It doesn't necessarily mean that the limit does exist or doesn't exist. We just don't have enough information to determine it at this time. So that was one reason we spent so much time focusing on doing examples where direct substitution gave us 0 over 0. Well, let's look at the formalized definition of a derivative, and we'll kind of walk through this, but there's nothing new based on what we have done so far. All right, if we have a function that's defined just to be y is equal to f of x, then we are going to define the derivative of the function at any value, and we're going to use this type of notation. The way we read this is f prime of x, and it's going to be equal to that thing we just computed. It's the limit of this difference quotient as h approaches 0. So one terminology for this expression that we computed is we call it a difference quotient. It's something that we kind of focus on as we try to evaluate what these derivatives are. So one more time, f prime of x is equal to the limit of this as h approaches 0. So the limit won't always exist, but when it exists, we will say that f is differentiable at c. And here's a procedure for how we can find the derivative using the definition. Now, I want to comment before we look at it. We're going to be using the definition in this video. In future videos, we're going to introduce just shortcuts that are well-established shortcuts for different situations. So the examples we do computing derivatives in this video are going to rely on the definition, and the work's going to be rather long and a little bit tedious at times, but in the future there will be really dramatic shortcuts that will reduce our effort that we need to spend. All right, but we're not there yet. So first of all, we always let h represent the change from the initial point to that second point. That's kind of just an implied thing. That would mean that the corresponding change in y would be the second y value minus the first y value. So then, and this is where you usually pick up in your work, you start by computing this difference quotient. It's y2 minus y1 over the simplified version of x2 minus x1. So this is the thing we compute, and we simplify it. After we have finished doing that, at the very end of the problem, we think about what would the limit of the difference quotient be as h approaches 0. And then that will allow us to determine what f prime of x is, which is the derivative of f. So just as a heads up, there are a lot of different there's a lot of different notation that we could use for a derivative. So f prime of x is maybe the most common thing you'll see, but you might also see it called y prime. You might see it called dy dx, which would just stand for the derivative of y with respect to x. You might see d dx of f of x, which would be the derivative with respect to x of the f function, or you might see it listed these ways. All of these sets of notation simply mean find the derivative of the given function. All right, all of our discussion up until now has been theoretical. Let's go ahead and actually find a derivative. In fact, it's already been found for us. Somebody is telling you that the first derivative of f is actually equal to negative x. We're going to use the definition just to verify that this is true. So let's go ahead and write down what the definition is. And when we work with this, we always start by examining the difference quotient, and that's where I'm going to begin my work here. So I need to compute f of x plus h, then I need to subtract f of x, and then I need to divide everything by h. Okay, so how does this practically play out? We have 9 minus 1/2 x squared. So when I compute this first part, which is f of x plus h, I'm substituting x plus h into the f function. So we're just replacing x with x plus h. All right, so let's do that here, x plus h. That's the first part. Now we subtract, and it says to subtract f of x. So I want to subtract f of x here. I'm going to put parentheses around it because we have multiple terms that make up f of x, and we want to make sure that we subtract all of them. Then this is going to be all over h. Okay, now that we've done that, we want to simplify. It's very standard to see x plus h quantity squared in the middle of your work. If you've not thought about this recently, the way you would figure out what that is you would just expand it out. You get x squared plus xh plus xh plus h squared, and that's equal to x squared plus 2xh plus h squared. Now this is so standard that I'm not going to write this down in future examples. I'm just going to reference that like this is the answer that you always get when you try to figure out what the quantity of x plus h squared is. Okay, so how do we use that? I'm just going to simplify. This is 9 minus half of, okay, now I'll substitute that in, x squared plus 2xh plus h squared minus 9 minus 1/2 x squared. I haven't distributed anything into parentheses yet, but now, in this next line, I'll go ahead and do that. So we get 9 minus 1/2 x squared. Continue distributing the negative 1/2. We get negative xh minus 1/2 h squared. Then when we distribute in the next set of parentheses, we're distributing a minus sign, so we get minus 9 plus 1/2 x squared. Okay, still everything is over h. And what you're going to notice in this line is there's going to be a lot of reducing that happens. So the positive 1/2 x squared and the negative 1/2 x squared is just equal to 0. The minus 9 and the positive 9 is just 0. So all we have left are two terms. And let's go ahead and write those down. We have negative xh minus 1/2 h squared over h. If you recall, remember when we dealt with limits, in situations like this, if you tried to put 0 in for h, we're not there yet, but if we tried, you would get 0 minus 0 over 0, which is just 0 over 0. So one strategy we had was we factored h out of our numerator, so then it could reduce with this down in the denominator. And you're going to see that happen in all of the examples today. So we factor out an h. What we're left with is negative x minus 1/2 h, and then this is over h, and then we can reduce, cancel out that h that's in our numerator and our denominator. All right then, so everything we've been doing is we've been examining this difference quotient up here. So now that we've figured out what this difference quotient is equal to, we now need to think about the limit of the difference quotient. So let's go ahead and write that down. What is the limit? H needs to approach 0. And what am I looking at? I'm looking at this thing I just computed. And when you plug this in, when you use direct substitution here, 0 gets plugged in for h. We just leave the x alone. So what we have is we have negative x. Technically it's minus half of 0, but the half of 0 just disappears. So what we have is we have this equal to negative x. I didn't write down the derivative notation, but probably it would have been a good idea to do that. F prime is the thing that we just computed. So f prime is the derivative. It's equal to that limit. And then our final answer was negative x. So we've done what they asked. We verified that f prime of x is actually equal to negative x. All right, once we have that, we can then ask a number of follow-up questions. So first of all, find the instantaneous rate of change of the function at x equals 2. Something I like to point out is that right now, because of what we just did, we really have two different functions. We have the original function, which you see up there at the top of the screen, f of x, and from it we computed its derivative, which is a separate function. The derivative function computes the instantaneous rate of change of the original function. So this question says, what is the instantaneous rate of change of the original function at this point? We are going to take 2 and we are going to plug it in to the derivative function because that is the thing that's computing our instantaneous rate of change. So we want to compute f prime of 2. That means just plug 2 into f prime, and what we get is we get negative 2. So we have the instantaneous rate of change. All right, continuing down in the notes, we define what a marginal revenue is. So in previous sections, previous videos, what we have looked at is we have talked about marginal revenue for linear functions, and the marginal revenue for a linear function is just the slope of that function. Well, when our functions get to be more involved, they don't necessarily have a slope, but the equivalent and the thing that we will be focusing on is we could think about the derivative, which is the rate of change of the function at a particular point. So the only thing that changes here in this definition, when we're talking about marginal revenue, the function will be naturally labeled as capital R. So R prime of x would be equal to this same limit, h is approaching 0, of the difference quotient. We're just referencing the R function this time. All right, this lets us go into the next example. So suppose the total revenue function for a blender is R of x equals 36x minus 0.01x squared dollars. Here x is going to be the number of units sold. What function gives the marginal revenue? So when you see this question, marginal revenue, that is a keyword that just tells you you need to compute the derivative, r prime of x. Now, in future sections, as we get farther into this course, we are going to have shortcuts that really abbreviate this computation. So in one line, you will be able to use, it's called the power rule. We will be able to just figure out what the derivative is. But we haven't developed it yet for the class, so I'm not using it yet. We're still going to rely on this initial just limit definition of a derivative. All right, this time my function is labeled as r, so when we write down the derivative, it would make sense to call this r of x plus h minus r of x. If you feel more comfortable writing f, it's totally fine to do that. Sometimes I will accidentally do that. Sorry, this is not over x, it's all over h. Okay, we now start just that same process again. So this time I'll do a little bit of highlighting just to kind of illustrate like where I'm at in the process. First of all, we need to figure out what is r of x plus h. So let's go ahead and do that. This is 36 times, we're putting in x plus h into the r function, minus 0.01 times x plus h, and that was squared. So what we have here what we just wrote down, like this is r of x plus h. All right, the next thing this tells me to compute is I need to subtract r of x. So let's go here and let's do that. This will be minus 30, so parentheses, 36x minus 0.01 x squared. And just to emphasize that, like, we have just subtracted r of x. All right, this still needs to be all over h. I'll try to write that really small so I have enough room. Now we need to simplify things. So you can distribute stuff into parentheses if you would like to, except for right here, when you have x plus h quantity squared, we do need to rewrite that. So I'll distribute at the beginning 36x plus 36h minus 0.01 times, I need to figure out what x plus h squared is. But we did that on the previous page. It was x squared plus 2xh plus h squared minus, I'll distribute the negative sign into parentheses as well. So this is minus 36x plus 0.01x squared. Do keep track of how this negative sign affects everything inside of those parentheses. All right, this is all over h. So then we now have a little bit more simplifying to do in our numerator. We have one last thing to distribute. Mostly things are just staying the same though. Minus 0.02xh minus 0.01 h squared minus 36x plus 0.01 x squared all over h. Now what we're expecting to happen is we're expecting a lot of stuff to reduce. We're going to scan through the problem. I see a positive 0.01 x squared and a negative 0.01 x squared. I see a minus 36 and a plus positive 36. Everything else that has not reduced all has an h in it, which is really good for us. So let's go ahead and write this down. We have 36h minus 0.02xh minus 0.01h squared. That's currently all over h. What we did in the previous example, we just keep following that pattern. We want to factor h out of the numerator. We get 36 minus 0.02x minus 0.01h. And then because it's all over h, the next thing that just always happens is that h reduces out of our problem. Now, remember that a derivative is a limit of this quotient. So we do need to use this limit notation. It's the limit. H is approaching 0. And then I'll just write down like what I was looking at. We need to put 0 into 36 minus 0.02x minus 0.01h. And when I do that, what I get is 36 minus 0.02x. And that finishes our derivative. I made the same like kind of careless error I did last time. I forgot to label this at the beginning. So at this step, as soon as you write down a limit, like this is when you can use the r prime notation. So my derivative is literally defined to be the limit of the quotient that I just reduced. So I'll use this r prime notation. That's our derivative. Okay, so we've done it. Part B, what is the marginal revenue when 600 units are sold? Well, the function I just computed, r prime, is marginal revenue. So the natural thing to do here would be to compute r prime of 600. This is equal to 36 minus 0.02 times 600. And I find that this is 24. It's a good idea to label this number. Marginal revenue always has the same label. It's always going to be dollars per unit. We want to say what this means. So if you think back to what derivatives compute, the derivative is an instantaneous rate of change of the original function. So this number 24 is a measurement of how quickly your revenue function is changing. Now, a way to make this feel like really hands-on is you can just think about what would happen if we move from one specification of production to the very next possibility. So if you are currently producing 600 units and you decide to increase this by 1, the next unit you produce will increase your revenue by $24. So let's write that out in a sentence. Increasing production by 1 unit will result in an increase of $24 in revenue. Now, if that seems like a little bit hand-wavy, it can feel really tangible if you take out your calculator, plug the number 600 into the original function, see what you get, then plug the number 601 into this original function and see what you get there. And what should happen is those two numbers are going to be almost exactly $24 apart. All right, we have a couple more parts that we want to answer to this question. In part C, we are asked what is the marginal revenue when 2,000 units are sold? Well, the marginal revenue function is r prime. We can plug 2,000 in it and see what we get. This time our answer is a negative number. It still has that same label. This is dollars per unit. And the implication of this is the same thing that we just discussed. If we increase production by 1 unit, this will result in, this time it'll be a decrease of $4 in our revenue. And like I said before, if you want to just make this feel really tangible, plug 2,000 into the original function, then plug 2001 into the original function, and you should see that you have a loss of $4 in revenue. All right, final question here. What is the marginal revenue when 1,800 units are sold? Well, the marginal is r prime. Let's plug 1,800 into that. When we do this, you're going to see that you get $0 of marginal. So $0 per unit. And then the implication here, let's write it out, is that if you sold one more unit, you would neither increase nor decrease your revenue. Okay, so we've finished the example, but it kind of previews an idea that we are going to be focusing on a lot later in the semester. So what we saw in part B was that if you plugged in 600, we had a positive rate of change of our revenue function. Then if we jump down and plug in 1,800, we have 0 rate of change in the revenue function. And then if we continue on to 2,000, we suddenly have a negative rate of change of the revenue function. All right, so let me write this down. We have a preview, without spoiling too much, hopefully. The idea here is that we have an underlying function, and we have three different numbers that we just plugged in. We have 600, we have 1,800, and then we have 2,000. And when we figured out the rate of change at 600, it was increasing quite rapidly, and somehow by the time it got to 1,800, it had kind of plateaued. It wasn't increasing or decreasing, and then over at 2,000, it had started to decrease rather slowly. So what we're going to be interested in later on in the semester is being able to look at something like this, or really look at this type of work, and we'll realize that this describes a local maximum. So if you increased and then plateaued and then decreased, the only way to do that was if you had a maximum revenue here at 1,800. Now, if you think too hard about it right now, you're not going to be impressed, because the original function was a quadratic, and we have algebra formulas that would compute the vertex of a parabola, but that's very specific to that type of function. So later on, we will look at cubic functions, or any kind of function that has a derivative, and we'll be able to answer the question, does this have a maximum or not? And that's something that calculus can do for us that algebra really could not have done for us. All right, let's look at another example. So in this example, we want to compute the slope of the tangent line to a graph at any point. When you're looking through a word problem and it asks about slope of tangent lines, this is just a phrase that references the derivative. So one of the interpretations of a derivative is it gives us slope of tangent lines because it's computing a rate of change. So this is just basically telling you to compute f prime. All right, following this same procedure we've been doing in the notes, let's go through and start with the difference quotient. We want f of x plus h then we'll subtract f of x, and then this will be all over h. Okay, we start by plugging in x plus h into the function. That takes care of f of x plus h. Now we subtract f of x. And this will be all over h. We start simplifying. We get x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x. This is all over h. We expect that things are going to reduce. Minus 3x plus 3x minus x squared, positive x squared. We scan the problem and notice everything has an h that's left, so we're going to factor that h out. What we're left with is 2x plus h plus 3. This is all over h, and then you'll reduce the h out of the problem. Finally, we finish by saying the limit h is going to approach 0 of the thing we just computed, and when you plug in 0, you get 2x plus 3. So even though like the process is kind of long, it doesn't have to take you very long, like when you get like really used to what it is that we're doing. Having said that, in the future it will be even shorter because we're going to have shortcuts that allow us to really abbreviate things. Okay, so we have come up with an expression that's the slope of a tangent at any point. Okay, I've done this every time in this video. Let's label it. F prime is what I just computed. This thing is f prime of x. All right, what is the slope of the tangent at a particular point? So keep in mind here that when we label a point like this, this is an x value and a y value, and your slope is not dependent on the y value. It's only dependent on x. So when we compute the slope, m is going to be equal to f prime of negative 1. Just simply meaning I'm putting negative 1, that's the x value, into the f prime function. When we do that, we get 2 times negative 1 plus 3, and I find that 1 is the final slope. All right, now that we have that, we can go ahead and we can write an equation of a line that's tangent to the graph at that particular point. And then let me just scroll down so that we see the final question as well. Okay, so an equation of a line can be given by y minus y1 equals m times x minus x1. There are other equations of lines like y equals mx plus b. You can use those, but they kind of obfuscate what's actually going on here. So the point of using this line is that you can write y plus 2 is equal to 1 times x plus 1. All right, I'm trying to color code this just a little bit. The significance of this formula, like this is the answer, that's all you have to do. It shows you what the y value and the x value were that you used. It also shows you what the slope is that you computed. So it's really easy to look at this and you know exactly what the point is and what the slope at that point would be. So graphing the line and the original function and the tangent line, let me go ahead and copy down what the original function was. Without getting too much into like the weeds here, we would have an x-intercept at 0. We would also have an x-intercept at negative 3. It's a parabola that opens up. We've actually already been given a point that the function goes through, which is up here. So at negative 1, negative 2, we would also have a point. So we just need to draw a parabola that opens up that kind of hits all of those. Okay, not a perfect graph, but it's fine. So what we just graphed was f of x. Then we could draw in a line, which would be this line, that goes through the point, negative 1, negative 2, and it needs to have a slope of 1. So something like this. Again, this is just a rough sketch, but the idea of what we have just computed, let me label this as the tangent. The idea is that you had a graph, we were given a point on the graph, we were able to compute the exact slope of the line that would hit that graph at exactly one spot. All right, let's talk about interpretations of a derivative. So all of these interpretations spring out of the idea that the derivative really is a rate of change. So if you were looking at an object that's moving in a straight line, what is the rate of change of an object? It would be its velocity. If you were looking at a function, the rate of change of a function is just the rate of change of the function. If you're looking at a revenue function, the rate of change of a revenue function would be the marginal revenue. And one other interpretation is if you're looking at a graph of the function, then the rate of change of the graph of a function would be the same thing as the slope of a tangent that's of the graph of the function. Okay, so basically all of these bolded words are keywords that would just let you know in the context of any problem, like if you need to go find a derivative as part of your process of solving it. We end this video with just a brief discussion about differentiability and continuity. We're not going to get into the weeds much here, but the relationship is that in order for a function to be differentiable, it must be continuous. But being continuous in and of itself is not enough to say that the function is actually differentiable. So we look at this first graph. This graph is not continuous, so it cannot be differentiable because continuity is necessary. You look at this, and if you even tried to think about like what is the slope of this graph at the point C, on the left it looks like a negative number, on the right it looks like a positive number, but because it's not continuous, it wouldn't be differentiable. So what this example illustrates is that continuity is necessary for differentiability. When we look at the next example, you have a continuous function. So you might think, well, maybe since it's continuous, it has a derivative. But at this point C, we have this like sharp edge. So if I asked you, what is the slope of this graph at this point C? Well, on the left, it looks like your slope is a -1, all the way up until you hit the point it's a -1. And on the right, maybe it looks like our slope is a +1. So you can't average those two numbers together and say, well, maybe the slope is 0. No, it has to be the same on the left and on the right for this derivative to be defined. That's the idea of a limit. So as we approach from the left, it looks like the slope was -1. As we approach from the right, it looks like the slope was a +1. So the derivative, which is a limit, is not defined. So the function is not differentiable, and this example illustrates that continuity is not sufficient for differentiability. When we look at the next example, what we have is we have a graph that has a vertical tangent line. Now, visually, it can be pretty hard to tell if it's actually like exactly a vertical line or if it's just like a really steep slope. So this would be something that you really would have to have the equation to determine. But if you ever have a graph that has a vertical tangent line, remember that one interpretation of your derivative is that it's the slope of a tangent line. Well, we know that the slope, m, is undefined. So your slope is undefined, the derivative would also therefore be undefined. Is kind of that relationship. Another way a vertical tangent might look is it might look like this here. Again, it's hard to tell if that's just a cusp in the graph or if really it got so steep that it was actually a vertical tangent line. But this is very clear that it's not differentiable because it looks kind of like example B. If you have any kind of a sharp corner or a cusp in your graph, definitely not differentiable. Okay, so one way of phrasing some of what I just said is that if a function is differentiable, then it's continuous. But notice that's not a two-way implication. Being continuous does not mean it's differentiable. It's just that if it is differentiable, it would therefore have to have been continuous. All right, that's the end of this video. Hopefully that is helpful.